Let's mimic a typical hospital supply room. We have 4 supply racks, multiple items, labels are small, items are really stacked, and your visibility is moderately limited because of the bins that most of the supplies are in. You need to find the oxygen mask. Let's also add a scenario. A patient's life is at stake and the time required for you to get the item is limited. 10 seconds, go. And that's the reality that hospital clinicians have to navigate every shift. But because of our AI-powered hospital supply retrieval system, we were able to decrease retrieval time, which in turn helps clinicians save lives.
Hey everyone, I'm going to be taking you through how did we get to the design that we have today, and I'll be doing so on Figma, so follow along. So first of all, we started by putting ourselves in the shoes of the clinicians, and we said, if we were a clinician that didn't know the supply room, what would we need in order to help them? We started off with some initial wireframes, initial architecture. As you could see throughout all these brainstorming sessions, including the design of the LEDs, defining subsystems and designing tests for each one of them, we came to what we have today. And then we have our Gantt chart, which was heavily used to plan out how this all comes together to design it. Now, our system at a high level, how it works is a clinician walks into the supply room, they talk to our Raspberry Pi, which is equipped with both the mic and the database. Now, the Raspberry Pi picks up keywords and matches it to the database to figure out which item was requested. Once that's found out, it pings the correct rack via the Arduino and Bluetooth Low Energy. Then the Arduino triggers a speaker and the LEDs to pinpoint the exact location, both by sound and visually for the user.
All right, so this is the receiving end of everything. Basically, this is the rack subsystem. Each one is comprised of an Arduino in the bottom left, so 4 Arduinos total. And then you have 4 strips of LED lights. Now, the Raspberry Pi communicates to the Arduinos, and it basically tells them in 80 bits, in 80 slots per rack, which ones to light up. So the Arduino takes that information and then runs a calculation. Now these are running on a 512 kilohertz clock. And basically what the Arduino does is send a specific signal that each computer within these LEDs gets its information from, and it knows when to light up.
So this is the setup for how we measure our power. Basically, we have the entire Arduino circuit here running off the batteries, and in between the batteries and the rest of the circuit, there is an amp meter, which we can then use to calculate power.
So this is the UI for our Iris system. It is all running on the Raspberry Pi. The Raspberry Pi has a hotspot that I've connected to here, which allows me to access the UI. Here we can view our different racks. So if we go to rack 1 here and we click on an item, we can see the item information at the top, and we can also edit the items here. You can also make the item smaller as well as larger, depending on the amount of space that it takes up. Here you can view the connection status to the Arduinos as well. As they connect, it will tell you that it's connected. You are also able to view all of the logs and the changes that happen within this database and within the system in general. Within the Raspberry Pi is where our database is stored, and this is where all the items are going to be located. So the items are going to have the corresponding rack number that they're in, the corresponding slots that they take up, as well as the item name itself, any of the tags that are associated with it, which would be any of the grouping, and then also the other names that you may put into it. For our voice recognition model that's stored in the Raspberry Pi, we are using VOSC, which is a local and not on the cloud model. What it means by local is that it is only stored on the Raspberry Pi, so it's not using any external training, it's only using what is on there. The way that we decided on VOSC was through analysis of some different offline models. So we compared VOSC and Whisper, and we can see here that the results showed that VOSC did do better than Whisper. There were a few reasons for this. One of them is that Whisper had a hard time with the short phrases that were said, and when you walk into the supply room, more than likely you're just going to say one word or item. For our UI, we're using the Flask framework, which allows us to create the UI and have API calls that are simple, go from the Raspberry Pi to whatever you're using that UI on.
and then our voice commands. So it'll go to the UI microphone, get processed within the Raspberry Pi, and this is where our NLP model, VOSC, is going to be used. This parsed request will then go through the database. It will match any of those items that are in the database with what was heard, and then if there is a match, it will ping the Arduino with the correct location.
Before we committed to a design, we needed to identify the applicable standards. IEC 60601 governs the electrical safety for medical devices. Since Iris continuously draws power from the wall outlet, we need to make sure that our design never put the patients or clinicians at risk. IEC 62366 is a requirement for us to make sure that the design we made decreases user error as much as possible. For example, creating a UI that is intuitive. ISO 14971 addresses the risk management for medical devices. This standard ensures that the installation, the use, and maintenance of Iris is all done in a way that minimizes harm to a user.
We decided to have our LEDs in the tubing attached to the clamps so that we can easily attach and remove our LEDs from the rack without having to physically stick the LEDs onto the rack itself. If something were to happen where one side of the LEDs go out, we can easily remove just the one shelf and replace it with a new one instead of having to replace the entire system. To build our clips, we use TPU 98, meaning that it has a good level of flexibility while still being stiff enough to easily be taken on and off the racks.
Another component of our project was making housing units for our microcontrollers. For the Raspberry Pi, we needed something to be big enough to hold the fan that's attached to the Raspberry Pi to cool it down. As well, it needed to have ports so the microphone could be plugged into it, and then a housing for that was big enough for the microphone. For our Arduino, we needed something that can be attached to the racks, and then we also needed the Arduino to be easily accessible. We can access it as well as recharge the battery pack that's attached to the Arduinos.
For our budget, we spent approximately $1,500 on our shelves and our wheels, and then we also spent about $1,500 on the actual hardware components that we used to make our 4-rack system. So this puts our cost at about $495 per unit, but this doesn't take into account that we do have extras of some of our supplies just in case we need them or need to replace things.
So in order to test our design, we took it to Aztec, which allowed us to simulate what would happen in a real scenario with real clinicians. Our first simulation was we had 8 nursing students come in. Some of the things that we learned from our first Aztec was that our software and hardware connection failed a few times, which led to complications. Some of the volunteers have never done a simulation before, and it was hard for them to follow along. So what we did was we took our simulation and simplified it at a second time at Aztec. For this one, what we did was took that and put it all into a tabletop scenario is what we called it. In these cases, the clinician had to, into the supply room, get one item, walk back, and then get a group of items for some procedure.
These are the system requirements we successfully passed, failed, and that are still in progress. Requirements 3.1 and 5.3 are marked as in progress because at the time of this recording, we're still processing data from Aztec and finalizing those results. The LED activation failure under 2.3 is because the NLP processing is taking longer since we are using a larger model, introducing too much latency. For future iterations, maybe upgrading the hardware seems to be the key deciding factor in properly supporting our more advanced NLP model VOSC. But we believe the biggest game changer for this product/system would be integrating barcode scanning to automatically populate item information during restocking, which would basically streamline the workflow for clinician staff. That concludes our Team 26050's video, and we hope to see you at Design Day.